Okay, guys. So good morning. This is Make Club, and today's session is, like most of you already know, but it's like basic robotic principles, why we have robotic arms, and we will go an overview and just try this to make the simplest sketch that we can do with grasshopper for controlling a robotic arm. You will say, okay, robotic arms, like the second week of the academy, is too early. Yes. Why? Because the robotic arms have not content included in the academy, neither in them dev. It's a personal push that I do because I think it's good as exploration tool because it's really multidisciplinary. Um, Robotic arms, generally speaking, are more like industry grade, like data fabrication elements, and by so there's like professional equipment. Like most of them are like the cheapest you can buy is 15,000 euros. For example, that one is 100,000 euros. So we start already with a big, huge push. So as we have the possibilities and you have the possibility to touch this kind of expensive equipment, and you can do it like when you're in hands, and I think that it's really fair that you try to use it as much as possible. Like not everybody we have access to robotic arms. It's not nowadays. It's not that weird, but in general, it's weird to find spaces that have like 5 robotic arms as we do. Robotic arms, you will see, this presentation is a workshop we did like just 1.5 months ago that we teach another like Fab Lab that just bought a robotic arm. We teach them how to use for FDM 3D printing. FDM 3D printing is what you traditionally know as like normal 3D printing, like plastic extrusion. In this case, for example, this is the big KUKA, this one, mounted with a pellet extruder. That is basically it takes plastic particles and you print as the same as you do in like small printers, but a larger scale with larger nozzles and more volume. Basically, we print more or less 1 kilo an hour. Usually, like normal 3D printers, they print around like 80 grams an hour. So we are multiplying by 100 the amount of plastic, and by so, but they are not only for plastic. Robotic arms actually is one of the most like customized tools because allows a lot of freedom. What we will go over today is we will understand the principles of robotics, what are they meaningful, and when to use it. Because a lot of people say, hey, I will jump to the robotic arm. But you don't need to use the robotic arm. You can use, for example, that machine that you have there. Basically, it's a big 3-axis machine that we just made it so you can customize it. Now you don't feel comfortable, but at some point at the middle of the course, if you want to test, for example, you want to test the camera thing. It was you, not the camera final project. You want to test something with the camera and you want to do it in a controlled way, experimentation, or you want to, for example, some of you want to put like bioplastic over a fabric. You can do it with that machine. Want to use the machine or use a robotic arm will depend on what you want to do and how you want to do it. Not, for example, those machines can only do Cartesian movements, X, Y, Z. Sometimes you need to angle what you want to do. You need to introduce like 4 degrees or 5 degrees of freedom. In that case, either you use a 4 or 5 degrees of freedom machine or you use a robotic arm that they have in general 6 or 7 axes. So why this is going so slow? So for example, this, what is this? This could be done with a normal 3D printer. Yes, no? Why we use a robotic arm in this case? First, it's big. Second, having usually one of the problems with machines is you need a machine bigger than the object that you want to build. So if you want to build, for example, this, you need a machine bigger than this. Usually it's weird to find machines like that. And when you build a machine like that, they start to become really expensive. Why? Because they need that degree of accuracy. You may want to make big stuff. It means you need big motors because you need to move a lot of material. So if you have a robotic arm, you can compensate because it's a tool that can do almost everything. So it's a really customizable tool, and what you do can depend on basically what you want. I always make the comparison like a robotic arm is as silly as your arm. Some people are painters, some people are sculptors, some people are drawing, some people like they don't do anything, they put the finger on the ear. So they can do the same, depends on what you grab. And that is actually the tool, what is called the end effector. For example, my arm, grab this, I can be a 3D printer. If I grab this, I can be a doctor, like putting vaccines on people, like for example. So the same happens with robotic arms. So most of the times you want to do a specific process, you don't need to build a specific machine, but you can use it like as a multi-tool. In this case, why we use this one is because the pellet extruder is around like 15 kilos in weight. That's a really heavy tool. So actually the only one that can lift is this one. Neither the small tool, the small robotic arms can lift it. It's too heavy for them. What happened here? It's loading. This case, for example, this is also plastic printing, FDM printing. But you see that it's tilted. This is called non-planar 3D printing. When you print something, usually you're doing layers. You make slices, and you make one layer, another one, another one, another one. But all the slices is in the same plane. In this case, it's not in the same plane. The plane is a three-dimensional surface. So with robotic arms, it's really easy to do non-planar 3D printing. With traditional machines, can we do non-planar 3D printing? Yes and no. Depends specifically on the machine that you are using. Why? Because if you print in a tilted surface, what happens, for example, with this? This is a plastic printer. It hits. With robotic arms, basically we can tilt, so we avoid collision. So actually we can tilt the orientation, so we can print three-dimensionally without having collisions. Collision is one of the most dangerous things that happens to any manufacturing equipment. That could happen with a 3D printer, a laser cutter, and CNC. Actually, in CNCs is one of the things that the CNC machines do, is check for collisions on machines, on big complex CNC. So one of the benefits of robotic arms is that we can do non-planar printing. And we can do huge things too. For example, this is printing non-planar and a big thing. Actually, this tool is just hanging around there in the exhibition. As we can do big stuff, we can also do it, for example, we can print thick. In this case, we are printing with a 3mm nozzle. 3mm nozzle, it means you need a lot of material to push. And you see the plastic boxes that are just there. Those are plastic pellets. That is basically plastic crushed, industrial grade, and then you feed. Instead of having a roll of filament that is the same as you have here, that is what's usually mainly used in FDM printing, you use the plastic material, the virgin material that they made these guys. And actually it's funny because how to make this filament is using this tool. They put this tool in horizontal and they start pulling the plastic in a line. And they measure with lasers to control the diameter of the filament. So actually the filament makers are pellet extruders. So it's like you can jump one step back and use it for that process. What I'm focusing a lot in 3D printing, because it's the first exercise we will do in 1, 2. So next club is code club, and next one is plastic recycling. The third, in 3 weeks, we will go on to non-planar 3D printing because it's 3D printing week. And to keep like the line with the club, you will learn how to use the FDM printers, the SLA printers, other kinds of 3D printing, for example, basic printing, and we will try to 3D print in non-planar. I will say try because it's not that obvious, and most of the times it fails. You need to test, but you will get hands-on experience. So for being able to do that, today we have to understand how robotic works and how to make simple files, really simple files. For example, these are some examples of what could be done, for example, with plastic extrusion. In the case of in 3 weeks, we will not use the big pellet extruder. Why? Because it will be more. It's the first time you touch robots, and probably it will be failures. And basically, we don't want to waste like 20 kilos of plastic. We will do with a small pellet extruder, like filament extruder that is the same that you find in the machines, but adapted to robotic arm. Also, it's like less dangerous, it's portable, and it's easy to use. But that doesn't mean that you cannot create complex geometries like this one that is not used traditional slicing programs. Let's go. What else you can do, for example, with a robotic arm? This is usually one of the first exercises with robotic arms, that is basically putting an LED and make it, the machine, draw in the air. And you take a long-term photographic excursion. Ideally, in 2 weeks, during the first half an hour of the class, you will have already the files ready. We will do like a few light painting and then jump onto non-planar 3D printing. And you will see that usually from now on, the clubs are going to be really intensive. We will have to have the files and something prepared before class if you really want to spend time on using the robot. Like at the end, we have only 2 hours for this, and it usually takes time. Usually, sorry, this is a really long presentation. For example, here you can also see a lot, well, you see in live why they use, for example, this robotic arm for printing clay and not use a big printer. Because for printing, what they will do, they will need to use the building structure to actually print and use as a printer. And actually, some spaces, for example, the ETH storage is basically a big 3D printer, building size, and then they put the cover and the roof over the printer. And actually, the whole building is the printer. But that is like Swiss, they have like 20 million euros to build the printer. And it's weird. It's really only a few setups like that exist in the world. In this case, it's for printing big stuff because it's really affordable. And one of the big points is even the footprint size of the robot is not really huge. But the area of influence of the robot, in this case, is 2.5 meter radius. So that means you have a more or less a 5 by 5 working space. It's not exactly like that, but it's more or less a huge working space compared to the small footprint of a robotic arm. These are just few examples of things. Or, for example, what happens when you want to move a big machine? Robots have a parking position. Actually, it's the same as human. We have a position where we can park them, we put the brakes, and they self-collapse on themselves. So actually, the footprint of moving a robot could be really small. So it's a tool that is more or less easy to move compared to other machineries. And as they are not as accurate, for example, a specific 3D printer that has like microns accuracy, a robotic arm has usually less accuracy than a specific machine for that, has the ability that depends on the scale, you need accuracy or not. For example, if you want to print concrete benches, it doesn't matter if you have 1 centimeter accuracy or not. Actually, you will not fill in a public bench. This is, for example, for printing street furniture. And actually, instead of printing the furniture and then move it, it was easier to move the robot than the furniture because it was more lightweight. So actually, they move the robot, print on the middle of the square, and then move the robot back again. So actually, this is, for example, is also planar 3D printing. This is not non-planar. Or, for example, other things, other types of methodologies or processes that you can do with a robotic arm. Is, for example, wire bending. Did we have the video here? Yes. Ooh. So, robotic arms can do as many processes basically as you can imagine. This case was a project that was taking pipes and make the robot then turn on the steel pipe, have more complex geometry. This is, for example, the mock-up of this specific. Oh my God! Sorry, the video is very annoying. This one. This is a little rig that basically is like building your own tool for the table that works. Making this in a small, this side, this is as an MA17. This is this motor. It's really small. This is for bending a light metal. What happens when you need to bend like a 5mm bar of steel? The motor you need for that is really huge. So are you going to build a whole rig with reinforcements and etc. No, for example, you can just use robotic arm, but by defect, are industrial grade robot motors that are really, really powerful, can hold that amount of torque. Oh. So in this case, we tested with a small rig if the methodology of the process could be done, and use the robot to actually take the final codes that were difficult to test. So in this case, robot is grabbing metal pipe, putting in position, holding a metal piece, and bend it to place. Other processes, actually this process, for example, is done industrially for a lot of things. Is incremental seed forming. It's a process that is quite weird, but basically you mount on the robot like a metal steel bar, and you have a metal sheet that usually like 1 to 3 millimeter steel, and you start pressing a little bit, and as more times you do, the metal starts deforming. So usually you start from the center, they are kind of have these kind of spirals, and you do start doing spirals around to actually form your sheet. The process is really, really beautiful. Let's move on. As you see, for example, the robot here is quite cute. Why? Because, for example, this one is like a gear. This is pushing like 90, 100 force on the metal each time, just by pressing 1 millimeter or 100 kilos. It can do repeatedly a lot of times. So they bend metallic panels for doing what? For developing this kind of pavilion that is made of like 206 pieces of metal. This is doing the structural test, and this is, for example, doing the analysis. So each panel custom. Other processes, for example, in this case is foam cutting, like polystyrene foam cutting. You know that there are some cables, like maybe the ones that are architect designers, you make models by with a hot wire that cuts foam. No? So basically, it's doing the same with a like square that keeps the hot wire in tension, and basically you start cutting the foam to a customized shape. So, for example, with that, you can make custom bricks, because what happened with when you want to cut foam, you need to have like completely like 360 degrees of freedom. And not only you want to attach a piece of foam from, for example, from the left, but maybe also from the right. And building a machine that does that is a 5-axis machine. It's a machine that can rotate and move the piece all around. So in fabrication, either the piece stays and you move around, or the machine of the piece moves around. For example, that happens with complex CNC 5-axis fabrication. Happens, you have a metal sheet that is just turned around, and the motor that is cutting just makes a simple movement. In this case, for example, this was an art not only for fabrication, but this is an art exhibition. I don't know if it's a video. No. So robotic arms also has the ability that they are industrially grade. Have you ever seen a video of how like the cars are manufactured? Like most of the manufacturing plants are like 50% at least automatized. And basically it's like robotic arms, like doing all the time, a lot of jobs, but really, really fast. So robotic arms have the ability that they can move really, really fast. For example, this one that is really old can move 2 meters per second. That's a lot. It's really huge. Actually, that robot can break the wall if he wants, if you don't do it in a controlled way. So in this case, for safety, they use a small robotic arm that has a laser pointer, and they were playing a music, and it was like a kind of concert. And the robot was actually pointing with the laser the little balls that you see, like they were like these balls, and they were the notes. So each ball, when you light up, makes a different note. So the people were playing music, and the robotic arm were playing music, but instead of playing the instrument, we're just pointing with the laser to make noise. Or in this case, robotic arms were programmed to actually listen to the concert and start drawing the notes that they were listening on a piece of clay. This is for engraving. And you see here that actually has like 4 like fingers. That's also one of the benefits of having a really customizable tool. This is a hand. And then I could do more or less this, like Eduardo scissor hands, more or less. I can choose to use the scissor, or I can choose to use the pen. So I can mount like different tools at the same time on my head. I just need to choose which one I'm using every time. So in this case, it was the same. Each different tool was using, one was a point, another one was a flat part, another one was a triangle. Okay. This is painting, actually with robots. I'm not gonna lie, these processes are complicated. This is like 5 months of development doing this in life. I'm not gonna lie, but there are kind of things that you can do that, for example, drawing a line in clay, a custom thing, is easily done. Doing in life and make the process don't fail by using orchestra and etc. without delay is complex. Okay, so amazing what robots can do. A lot of things. How do they work? Who has ever used any fabrication equipment, like 3D printer, laser cut, or CNC? A few. Okay. Do we understand what is X, Y, and Z coordinates, everybody? Like it's the GPS, like front usually is X, on the side is Y, and the vertical is Z. Like basic space location. Most of the machines, they work like that. They have X, Y, and Z. And I will do this with a pen because it's just easy. This pen, I can move it like that. Yes, you say because you know how machines work. But actually my hand can also do this movement, and the tool is completely different orientation. I could be like that, and I'm still making the same movement. So we need to introduce the 3 rotational axes, A, B, C. Is A, B, and C. And each one is a rotational axe on the normal of the plane. So we have one rotational axe that is perpendicular to the axis. And robotic arms actually have a problem. Usually a machine has machines like this one. It's a really small machine. I will put here so also the people on the webcam can also see it. So we have Y, X, and Z. And how to make the movements for this machine is easy. One motor moves X. One motor moves Y. So we want to create instructions. We want to say, okay, move X10. This motor moves 10 steps, or like 10 millimeters, 10 units. What happened with robotic arms? What happened, for example, I'm the robotic arm. I have this location. I want to move 10 in X. Which motor do I move? Which one are my motors? My joints. What are my joints? Joint 1, joint 2, joint 3, joint 4, and joint 6, for example. It's a combination. So I need to move this one a little bit. But if I only move this one, I'm making an arc. So I need to open this one to compensate back. So actually it's a mix of movement between different motors. And that's what happened actually with robotic arms. As you have like several motors or several joints that are like A1, A2, A3, A4, A5, A6, usually you have a combination of motors. Producing the path of which motors to move and how is really complex. And there is where the control box makes the magic. What we do is we do inverse and forward kinematics. What's that? We just send the location of the original position and the final position. And between both, the control box does all the calculation on how the movement has to be done. It could be a straight forward movement, or it could be a translational movement. And actually, this is one of the most complex things on robotic arms. Do the inverse and forward kinematics. So, industrially grade, when you program a robotic arm for a robotic car factory, they program each one of the movements in a controlled way, and they do this by writing hardly the code. Like imagine coding, but with numbers randomly in the space. And actually, they send each angle position every time, because they need to control each one of the positions of the robot in a really accurate way. So actually, it saves motor movements, so the robot lasts longer, and also saves time. In here, we don't care about efficiency, let's say. We want about usability and how to make it easy. So we let the inverse kinematic box do the magic for us. So in order to program what we need to send every time, X, Y, Z coordinate, and the rotation plane, in which orientation is the object. The right-hand rule, that is the X, Y, Z, and we have the 3 degrees of freedom and the 3 rotational freedom. Robotic arms also have a particularity that they have like multiple coordinate system. Do you know what is a coordinate system? No, it's where the machine knows it is. Like, where am I? It's a location, basically. It could be absolute or relative location. For example, as humans, what is location? Like universe. Or we can be related to, I'm in this location on relation of this table. So we have absolute and relative locations. So for example, I am 3 meters away from you, but we are away like 2 meters from that door. Depends on which one is my origin, I am different distance. On myself, for example, I am not at any distance of myself. So in general, we consider like world origin as the robot origin, is the base of the robot, but that could be different. Then we have the tool origin. For example, the point of this, what is the origin of this? Depends. From you, it's at 1.5 meters, no? From me, it's at half meter, but from itself, it's at 0. So we can set up different origins and absolute coordinates. We have, in general, we have 3 types. We have tool, base, and robot. And when you design a path, it's important. For example, I want to move to this space, to this point. I can do it from this origin or from my origin. The numbers that I'm giving are different. If the robot I have said that I'm using the tool origin, the tool needs to move 30 centimeters. But if I'm using my origin, the tool needs to move like in an angle of 45 degrees, like 15 centimeters. It's different. So we always need to be careful which origin we use. This is the same. So in general, what we do, I'm telling you everything. Now let's close down and let's see what we use in general. We use tool origin. What we do is every time we mount a new tool, we do a 4-point calibration. That is telling the robot where the origin of this is. We said we're going to always use this as 0. And we're going to send a line. Let's say this is my my line that I want to print. So I want to print my line in a position that the tool can reach. Depends on the position of the robotic arm. And most of this is done hidden in a transparent way with the key forward and inverse kinematic controllers. So what we're going to do is send position whatever, 1, 2, 3. Origin is going to go to 1, 2, 3, and then to 1, 2, 4, and then to 1, 2, 4, and then to 5, 6, etc. So what you're going to do is match an origin of this to this.
Is it different for each tool? So
yes,
the tool is bigger or
yes,
relative to the height of the tool?
Yes, totally. So every time you change the tool, you need to do a calibration. Actually, how well you do the calibration also matters. Or in general, we do a calibration, what is called a 4-point calibration. That is, we move the robot in manual way. We have a kind of complex joystick. And if I want to do the calibration, yeah, we put a nail. Usually, like extruders are easy because they have a point. And what we do is we approximate and we save one position. Now we reach from another position and we save this point. And now we save this point. What we save is actually the rotor, the motor angles. And we save for each one of the positions. And we do 4 times.
So we position ourselves.
Yeah. Which position for in like that, the amount of rotation of each motor. And we save those values. We put the robot like that, and we save the position of each arm. With those values, we save them to the robot, and the robot does the inverse kinematics. That is determining from, you said that it was the same position, but they have stayed different rotations. So does all the calculation back to know where this is real. In case of a nail, it's easy, extruder. And you have like what is called deviance error. How well you do this matters. And the robot will state, you have like 3 millimeter tolerance. It means all your positions, it's impossible that they match. So the robot could be here or could be here with a 3 millimeter error mistake. And actually, if you do this well, it should be below 0.2 millimeters. But some tools are impossible to do. For example, a gripper. This is a gripper, robotic gripper. What is the center? There is no point. The center should be somewhere around. So depends on the tool, it's really difficult to do a point calibration. Industrially grade, there are some devices that does that for you, but usually they have the same price as the robot. And there is one that actually has some lasers, and it's like a ring of lasers, and the robot starts doing like this randomly. The tool makes magic and finds it for you, but it's like buying another robot for you. And this is what the robot does, the reverse path offset. So when you produce an object or a movement for the robot doesn't care if it's printing, extruding, putting light or whatever. You always need to send whatever is the position that you want to reach and the orientation of how you want to reach that position. So for example, for the robot, it doesn't matter if you want to print like this or you want to print like this. The robot is silly, doesn't know. But you know that there is a table, and if the robot does this, it means your plane is reversed. The robot is going to hit the table, probably break your tool and break part of the robot and the table. So we need to be really careful when we do virtualize and present the files. We double check always each one of the movements of the robot, so there is no one of the positions that suddenly is like crazy and is like that. And it's really important. So how we make the movements also matters. We have what's called movement interpolation. For example, I want to reach you. How I can reach that point? Ideally, if there was no table, I could reach straight forward. No, this is the start position. This is the end position. Or let's go easy. We want to reach ourselves. So initial position, next position is you. The simplest movement, what is? A linear movement, straightforward. Okay, easy. But that, sometimes for the robot, is not easy because it needs to make a weird movement. I will explain that. We can reach in different ways, like doing an arc, hello. Or I can do it maybe in, this is my best comfortable way, that is like, hey, what's up? This is how I can reach her. So robots happen the same. There are three ways of reaching movement to movement. Why? Imagine that I'm here. I want to move here. How I can do it? Straightforward. You see that I'm having like some troubles with my shoulder to keep a perfect line, no? Like I'm compressing actually my shoulder, I'm uncomfortable, and I'm reaching that point. What would be an easy way to do it? For me, I can do an arc movement. Ooh, I have reduced a lot of my joint movements. What's comfortable? What will be the more natural way for me? I don't know, like maybe something like that. Something that naturally will reduce all my movements to the minimum, but I have reached the position. So we have PTP, arc, and lean movements. Which one is better? Depends. Why? Because in PTP, you don't control the middle positions. That maybe is dangerous. For example, I have this on the table. I want to move to here. Obviously, I know that I have this one here. So I will send a third position in the space to avoid the collision. If I still send these three positions and I let it, okay, now you can reach this position no matter what, maybe the robot does like this and hits the object because I'm not setting in control how is it traveling in the air or traveling. And actually, that's better for the robot because it will reduce the amount of movements, it will do it faster, and will reduce singularities. That we will see what it is. But we have it's dangerous as we don't know exactly what the robot will do. In an industrial space, they try to use these movements because they're faster, they waste less robot, and in general they're better. But they're dangerous. For example, in our environment, we want to know where exactly on what robots the robot will do. Arc is like kind of semi-semi. It's easier for the robot, but still we can preview in a simplified way what the robot will do. It will make arcs between movements. Sometimes we also don't want that. In general, here we always try to use linear interpolations. That is, go point to point like in a more traditional way, just because they are easier to visualize, easier to preview for mistakes, and we can visualize on the preview on the computer what the robot will do on movement. And then we have singularities that are a little bit complex to explain. I have to be honest. So that happens when two axes gets aligned. And doing like that with an arm is difficult. But I will try to say, I want to touch it like that. I have this arm and this joint aligned. Which one I need to rotate? I know because I'm human, I have million years of evolution that this one is going to be easy. The robot is silly. Doesn't know if it is to rotate this one or this one in order to hit you. So that is a singularity. It's when two axes get aligned together. So in this case, for example, A2 and E3 are exactly in the same position. The inverse kinematics has problem to determine which one to move first or which one is better to move. And that, what is producing? In real, on the real world, what happened is actually the robot is moving, and you see that moving fast and suddenly slow down a lot. And one of the axes starts like rotating a lot on itself because it's trying to solve the problem, but doesn't know how to solve the problem on which axis to move first. Goes to the singularity and usually have warnings on the pendant. The pendant is the control of the robot. And it's telling you, close to a singularity, because it means your path is not optimized or has some errors. Depends on the singularity, it could be solved or not. But imagine that the control box needs to do a lot of calculations really fast to actually just to produce a small movement. So we always try to avoid singularities, and actually the reciprocal program that you use warn us of possible singularities, and we are able to analyze them.
Just all the singularities in the path you will use, it's not complete before. And the arm, I thought it was just receiving the coordinates or.
Yes, but at some point. It's not receiving each one of the individual movements. It's really similar to a file of 3D printer, like more complex, but you're sending one position to another one. And you are saying to the robot, use linear. So from this one to this one, I don't have the positions of the robot saved on my file. The robot control box is calculating all for that for us. So from here to here, there are some points that are undetermined, and we don't specify. The robot calculates for us, and you will say, okay, why don't we divide this with multiple points, and we have more control? We don't know why, but robots have a shitty memory. This robot can only save 2 megabytes file. Like you will say, like, come on, you're kidding. No, I'm true. I'm honest. Actually, this robot has a maximum point count of 30,000 points. This is at 60,000 points if you don't optimize. If you optimize well, it's 3,000 points. So actually reducing your file weight is really important. Why? Because the robotic arms, in general, they are meant to be industrially grade use. That means they do a simple task 3 million times. You don't need to save a lot of points in the space. I'll tell you what's that one's constraint. That's why the new generation of robots is improving that. But for example, a robot of, a robot of 5 years, for example, this one is 12 years. This is a KRC2. A KRC4, that is more or less 5 years, can only save like 60,000 points in the memory. Actually, memory is like useless. Most of the times you need to cut your file into several files and have an automatic loading of the file to solve that issue. Okay. So, first time we are on time. So now, how to control robot arms? I will show you first, while this opens, a few examples of what we can do more or less easy here. As I stated before, this is, for example, FDM, plastic printing, with a pellet extruder. We have one that I will not take it here because it's ultra huge and heavy. Maybe we can go there and watch them. We have, in the house, we have developed several tools because robotic arm doesn't have a tool per se. We have developed, for example, a drawing tool. That is a tool that takes pens and has a little spring. So when you click, you don't break the point of the tool. Why? Because, as I said before, you need to calibrate your tool. Sometimes you don't do it well, or the surface is not even. You as human, you know how to regulate the pressure. The robot don't. And sometimes you have 1 millimeter mistake that will break the point of your pen. So we have a drawing tools, like for pen and for brushes also. We have plastic printing, like traditional plastic printing, like this. What else we have? We have paste printing. Basically, it's like the clay printers, or you can do with a biomaterial, etc. I can show you, sorry. Paste printing. I can show you some videos of coffee printing, bio-based printing. Most of the things weird are here. This is a more or less old tool. We are moving to a new one. We have liquid printer. This is, for example, this. You print liquid inside liquid. For example, you're printing glue. Glue doesn't harden instantly. You need to let it in a material like floating or a semi-floating cell, so until it hardens. So that's called inkjet printing. So basically, this is like a big syringe with a motor, automatized, and you dip it in a bowl of gel. You print your geometry, you take it out, and you let it harden, and then you can like fish it. What more things we have? The depends on the density of your material. You need to make it in different things. Okay. One second, I need to look for the.
How is the tool and the robot arm aware of the position in space? Do these encoders that you deploy, or does it have another sort of?
Yes. So motors, the motors of most of the machines are like depends on the machine that we are talking, but what you can hear, they are divided in two types. Stepper motors, that are the simpler type of control motor that you send the position and the machine assumes the position will be reached. That happens, for example, with this kind of FDM printers. You send the position and they assume it will reach. If it hits something, you have the problem. The machine doesn't know, and that's why it fails. For example, we have steppers with encoders. So they have some sensors on the back that they read if the motor has actually reached that position. Then we have servo motors that you have used the servo motor like the angle one, like the Arduino one. Imagine this, but industrial way. The cheapest one starts at 500 euros in general. So those motors, they are like a complex brushless motor, brushless, plus encoder, plus feedback loop, and embedded in integrated electronics. We have one here. So we will have a class on this in the future, but for example, this is a stepper, this motor moves and doesn't know the amount of movement you have to assume that everything is okay. Then we have like the stepper with encoders. This is the same motor. The difference is this one has electronics in the back that is actually reading the amount of total rotations that we are doing. So in case the motor has not rotated, has been rotated 20 times and rotated 19, the electronics is reading that we are missing one step and compensates to rotate that step more than missing. Servo motors are similar to this, but like you can have a really good Volkswagen or you can have a Lamborghini. Like even if it's a good Volkswagen, it's still not the same. Like, there are differences. One is for like servo motors are high torque, they are lightweight, they are more accurate, they are best in everything. What also happens is you have the burn of crack. This industry base. For example, the Robotic laser there, they have servo motors as far as I know. That's why these laser cutters cost 3 times more than a normal laser cutter. The CNC, for example, doesn't need that amount of control accuracy. Yes, but we don't need to do it in that expensive way. We can use a servo motor with an encoder in case the machine needs one step to compensate that. And what is one difference between what we call open loop and closed loop? Machines that you send the movement and you don't know the amount of movement that you have reached is open loop. We just send the values and we assume that everything is working okay. Closed loop is we set the values and the motor or the final end actuator it needs to send a value back, confirm it that we have reached the position. Like that's why, for example, in the CNC, when we usually will see that on the computer, we actually see the light positions on the machine. And in case it has a deviation of more than half millimeter, the machine stops. There's something really wrong has happened, like you have a collision or etc. So robotic arms, for each one of the movements, has one of these such complex servo motors. Another thing that make it really complicated And one of the things that make them really expensive is this. Can you hold the motor? Okay, the motors have cables, and usually the robot arm has a lot of cables in them. So try to rotate 370 degrees. What happened with the cables? They are twisted. There's a moment you cannot twist. So actually they have a connector that avoids this. So it's a 360 connector for all the cables. And I have another connector. So actually you can rotate freely, endlessly. Robotic arms, usually like the axis, what is 6? Usually axis 1, 2, 3, 4 have limits. Usually the limit of axis 1 is usually like 270 degrees, something like that. Axis 2 is from here to here. it's exactly like that. So I usually do like that because it's easier to understand. Axis 3 is from here to here, almost 360, but in a vertical way. Then we have axis 4. Axis 4 usually depends on the robot, but usually like has 720. Can do 360 in one side and 360 in the other side. Then we have axis 5 and 6. That 5 usually is like 270 also because it collides in itself. Like this is the axis is like that, and we have the tool that hits the back of the arm. It's really similar to this bridge, no? Yeah. And we have axis 6. Axis 6 usually is the one that is 360. It is endless, infinite. But most of the times it's not activated by the effect because it's not needed. Usually you have like 360 in one direction, 360 in the other direction. So sometimes happen that when you don't do well the kinematics, you're moving one position and you reach the other position, but the robot is in the limit of the axis. That the inverse kinematics try to solve that kind of thing. Let's go a little bit on how to make simple files. I'm not sharing the screen, so let's share the screen. MDEF, I know that you have already, the ones that came to the club knows a little bit of Grasshopper. But Hub Academy, have you ever opened Grasshopper? Yes? No? Never? Okay. So this is going to be a little repetitive the first 10 minutes for the ones that know, but let's go over the basics. Rhino has another program inside or embedded, that is Grasshopper. Grasshopper is visual programming or visual scripting programming. How we activate and how we open Grasshopper. If you go to Standard tab, there is a green icon here that is called Grasshopper. You can either click this button or just type it, Grasshopper. With Grasshopper, you can do a lot of complex things, or you can just use the tools. For example, a lot of times I'm doing modeling. Rhinoceros doesn't want to do a Boolean subtraction because my model is not perfect. I open up Grasshopper, put the model in Grasshopper, do the Boolean subtraction in Grasshopper, and then come back to Rhino. Because it's another program and does things in a different way, I can fix it inside. For controlling robotic arms, it's mandatory and unluckily is the only way to use robotic arms in an easy way until you use like other expensive softwares. Is to install plugins for Grasshopper that does the inverse kinematics. That means we need to install a plugin inside Grasshopper in order to produce files for robotic arms. Grasshopper opens up as a, like, looks like a note. It's usually a hovering window. Like most of the people that run Grasshopper, they have like Rhino at full screen and Grasshopper on the right. Why? Because we use Rhino to visualize what we do in Grasshopper. Grasshopper has a lot of different options, and actually it's kind of Rhino but without visualizing. We have, like, for example, we have curves, we have vectors, we have surfaces, we have meshes, and each one of the components, we have different tools. We have analyze tools, we have form creation, for examples, we have create a cylinder, a cone, a sphere, and we have uh, object transformation, like trim, cut, etc. So, for example, we have a vector, we can deconstruct a vector. A vector to know what is the x, y, and z compounds of that vector. We can rotate, angle that vector. We can measure the amplitude of that vector. So, how we install plugins in Grasshopper? That is actually is mandatory most of times. Grasshopper by default comes only with a few components that are already powerful. But you see the list from display. All these I have here are plugins for doing different things. Plugins, what they do is basically take out complex scripts, like really lot of lines of code, and they put it in an easy format and package. So sometimes if you want to move an object from one position to another one, let's say I want to move this from here to here, in Rhinoceros, you take the model and you move it manually with a reference point or any 3D model program. But how you do this in a code? You need to create a vector. What is the movement vector? From here to here. So to create this vector, you need to create the origin point and the final point and say move in this vector orientation. There is a component in Grasshopper that instead of having to create 2 points, having to create a vector and then move, does everything in one component. So basically, just plugins in general, they make our life easier. Where are most of the plugins hosted, or where we can install them? If you go to Food for Rhino, this page not only has plugins for Grasshopper, but also for Rhino, that most of them there are free to install. So for example, we can look for Teco ABB. Don't point this point because we will install another one, but this is an example. Teco ABB is a plugin that will produce the tools and the model, for example, the 3D model of the robot, and let us visualize it and also do the inverse kinematic for us. And we can preview and actually, for example, Grasshopper for Grasshopper 4 and Grasshopper 5 win. Actually, this plugin is quite old. Before, we used to use this one. For example, if you want to use the Kuka, or let's say you want to do mesh, you want to do a lot of mesh modeling, like clay modeling in Grasshopper, you can also do it. Basic component to install is Mesh Edit. It will enhance the amount of tools that we can use for mesh. Actually, we have for calculating the mesh area, to calculate the mesh volume, to explode a mesh, to convert quads triangles. For example, the other day we talked about mesh could be triangulate. We can do the opposite. We can transform into quadrilaterals on a mesh. We can do it with this kind of tools. There are millions of plugins. I know. That's why we have in the Academy page, we have a list of the most used plugins. So it's in weekly classes, computer-aided design. What is last week class? Rhinoceros and Grasshopper is this one. Yes. Actually, you have like basic tutorials on how to model, put things, create simple geometries in Grasshopper. And then we have the basic plugin set that I already made it for you. I just download all the plugins, put in a folder, and you can download it. And you have simple scripts. And this is actually the first lesson we have with Ender. So let's see how we download a plugin set. Or let's say I have downloaded this one. I have registered. Okay, updated the conditions, really good. I don't care. I download this one. So we download a plugin. Usually plugins have some specific components. Let's extract them. Let's extract them. Actually, in the first folder, I didn't remember, but we have a plugin install guide in case you don't remember how to install the plugin. There is a note document on how to install it. We have two different kinds of components to install in a plugin. One of them is pufferfish. Yeah.
Which part of documentation?
Last week class, weekly classes, computer design, and you go to Rhinoceros Grasshopper. So for example, I have downloaded this pufferfish plugin. Pufferfish is for like natural modeling. It's pufferfish. It's super good, but it's complex. If you don't know how to model in Grasshopper, don't install it. Like it's overwhelming, but allows you to create this kind of geometries. Actually, I work with the guy that creates this plugin. This guy is called Michael Pryor. Michael Pryor is the head director of design of Nike for like the 3D printing new shoes and this kind of things. He's amazing in coding. So I create plugins for doing this kind of complex geometries. So when you go to the download folder, you have usually depends if the plugin is well done, has a README. If it not, has a green component and a folder with orange components. These components, you need to copy them in a folder inside Grasshopper. Where is that folder and where is located? Let's go on Grasshopper. You go to File, Special Folders, Component folder. Component is where you copy the green files, and you will see because they are green. So what you do is you copy this component. Actually, I will download. Probably is the newer one, pufferfish. Yeah, I have 2.8. I will download 2.8. So I will copy, paste it, yes, and I will go to take for the orange ones. Where does the orange ones go? File, special folders, user object folder. So we need to go actually copy the components in the green folder or the orange folder. You open the folder and all this shows up. You copy and you paste it. Did I copy everything or not? I will throw it. Replace. Okay. So now that I have installed the plugin, what I have to do? I need to close Grasshopper, close Rhino, and reopen the program. The plugin doesn't load until you don't restart the program. Okay, put this double screen. I open up Grasshopper. Now, Grasshopper takes a lot of time to load because I have a lot of plugins also. And for example, I have conflict just from the older component and the new one. So load the component, replace all, update the database. Okay. So what plugin are we going to use for robotics? And it's a basic plugin that you need to install. I need to look for it. Wait. It's called robots. Yes, robots. It's called robots plugin. For control robotic arms, there are multiple options. We have Taco, we have Kuka PRC, we have robots, we have Machina, we have Ex Machina. Here, we always try to use robots because it's a plugin that can compile for different robots. It means we can use for a KUKA, we can use a ABB, or we can use a UR. That are the brands we have. KUKA PRC, for example, is a plugin that works really well for KUKA, but we cannot save files for other programs, for other robots. That means, even so, it doesn't matter if you use one plugin or the other one, they all do the same. And what they do, they usually have some components like create a tool, load a robot, and we will not use this plugin for showing you because it's not, well, I will open up last day 5 I used the other day. Let's see if it's clear. Robot 2. Let me clean this a little bit. We need this. That's it. And positions, tool definition. Don't worry. It's going to be much easier than using. So first thing we're going to do is actually open up and choose a robot. That is, load a robot system. We need to select the robot we want to use. And you see here that opens up with a tab. This tab is a list of a database of different robots. And we have created this database actually between the Bartlett School, Theta, that is in Denmark, Grimsdijk, that's in London, like a lot of universities that work with digital fabrication equipment and have robotic arms. Between us, more or less, we share the same robots, but for example, the table where the robot is different. And we have modeled to actually make it easy for the students where the robot is. For example, in here we have EBR 140 and the KR 150. KR is KUKA, EBR is ABB. So ABR, for example, is this robotic arm. If we, for example, choose the KUKA, you will see the different size, no? That is green orange one. Let's use the EBR 140, and you will see that in the database will show 3 more. I don't have them because I have the old database. I don't care. For example, when I used to use the smaller one, I use this one. But you choose the EBR 140. That is the robot we want to use. So this will preload a 3D model. What else we need to define in a robot? Is the tool. I will put the full name so you see it better. Yeah, oh, it was full names already. By focus. By focus. Do you see well on the screen or I need to zoom more? It's okay? Okay. So we need to create a tool. What the tool is. Usually it's called the end effector. What tool we're going to use? Let's make a simple tool. Let's make just a cone, a pyramid in the robot as it was like a pen. Okay? Let's put a cylinder, not a pyramid. Okay. So we need to put the name on the tool. Let's put the name. How we create panels for having information in Grasshopper. We put panel, or if you double click on the main space, you put panel. Then you open up and you say like, my first tool. And we click outside. This is important because when you load the file to a robot, it gives you several warning messages. Like, one is the name of the tool. If by somehow you mistaken the tool, you can see before launching the file. So in case you have like long pen, it's not the same as short pen because the distance of the origin will be different. and the calibration will be different. So you can double check that you are using the correct one. Let's draw our geometry. I will hide the robot. I will disable the preview, and I will draw my tool. To make it easy, I'm going to do as much as I can in Rhino and use Grasshopper just for making the file. Seems okay? Okay, so I will make a cylinder with a base in the origin, 0. And I will make it like 50 diameter, I mean 5 centimeters, and make it 100 length. Okay, so this is my cylinder. I will reference my cylinder in Grasshopper. This is my tool. And my tool, we need to state what is the center, the point. Also, we need to know what is the point of the tool, where we're going to do the calibration, and the robot needs where it is. The tool, by defect, needs to be always in 0. What does that mean? You see the robot here. You see this is the flange. The flange is what holds whatever you have, what tool you have. The flange, the robot has coordinate systems. Which were the coordinate system of the robots? The origin. Okay, the robot is in the origin. The robot is in the origin. We see this is the X, Y origin, the main world origin. And what else we have? The tool origin. By defect, the robot has no tool. We're going to change it. We're going to put a new tool. The new tool is going to be a cylinder. We're going to place here. So right now we have a tool origin. The tool origin is here. It's a plane that is X, Y, Z. What we need to do is put a cylinder that has an origin plane in X, Y, Z, and we're going to build another point on top. So if this is another one origin that is tilted, where do I need to place my other geometry? In the origin, and put a point that is going to be the new origin. So now that I have my tool, this could be a cylinder or could be the 3D model of this. Well, let's start easy. So let's reference this geometry. Geometry is an empty component that we use to put things from Rhino to Grasshopper. So we right click and set one geometry. This one. Okay, selected. In Create Tool is asking for different things. Where is the TCP plane? TCP is how we call the origins, like the absolute and relative tool origins. Tool coordination point. That is a new origin. What is the new origin? It's a plane, no? It's asking for a plane, not a point. Why? Points have location in space, but they don't have orientation. A point has the all orientations. We need to really set what is the orientation. So this point, we're going to reference it to. Okay, point. And we set one point. This point. Okay. So this point is asking for a TCP. What is the TCP? A plane. How we create a plane in Grasshopper? You just put plane. But what plane do you want? What is this plane? What is the main, in which workspace we are right now? This one, the plane that we see is a XY plane. XY plane. If we put the plane, you see we have created another plane, a plane oriented in the space that is in this location, and the normal is the Z vector. So we put the plane. Okay, this is a new TCP. If we want to visualize the tool, the cylinder here is just for visualization purposes, so it's easy for us. We need to transform the geometry into a mesh. So we just put mesh, or what we do is we create, instead of a rep In Rhino, we create a mesh. Could be also. It's instead of this, let's do it like that. Let's create a mesh, a cone mesh, for example, base of the cone. This is a mesh already, so I simplify. We don't need this. We reference the geometry, and we connect the mesh. Now we have created the tool. We have set up the name, what is the new point, and what is the mesh. What else we need to create now? We need to create a target. Target is actually where the robot needs to go. It means the movements. Let's create a simple curve, okay? It's a curve, it's in the space, and I will move it a little bit up. Machines, do they understand curves? No. What do you understand? Position. And what is a position? A point. But that is in a normal Cartesian machine. You send points and the machine goes to the point because it has an orientation. What we need to send to the machine now? It's a little more complex than a point. It's a plane. Because what we are basically doing is the tool has this plane and we need to send another plane that the robot needs to match. So basically we want to do matching planes. So you construct first points and then you put planes on those points, the same as we did right now. Having a curve, how we do that? In a simple way. Let's make a little bit of space and let's reference the curve. Curve, set one curve. Okay, the curve is perfectly in Grasshopper. I will hide it. So from a curve, how we create points? We can divide the curve, no? Divide curve. Okay. How many points I want to create? Let's put a slider that say like, I don't know, 20 points. Now I can change it and reduce it, for example, to 3 points, like 5 points. Okay. Now that I have points, what I can create? Planes. XY planes. Okay, I just put the location of the plane here. Seems we're going well. It's almost done. We have the tool, we have the plane, and the plane. So actually the robot will try to match these planes. How we do this? We have assembled a robot. We have created the tool. We need to set up what? A target. Target is where the robot needs to go. It's like we need to construct the movements. The target asks for different things. One is the tool, because how you want to reach will depend on the tool. Okay, we need to set up a speed. How fast you want to go to those points, and how you want to move between those points. It's in millimeters per second. Let's be fast. It's test 100 millimeters per second, 10 centimeters per second, more or less is like this. What's the? Is what the robot is going to draw. The movement that the robot is going to do. Exactly. What else is asking? For a type of motion, let's not state it yet. And a zone, let's not state it yet. Like we have a lot of options here. Where display is. What we need to set up? The planes. Where do you want to go? We have created the planes here. So plane, you see, it becomes gray. and what type of motion we want to do between these points. Linear movements, no? So we have control, and the robot doesn't do like craziness. Type of motion. Okay. We have created the tool. We have selected the robot, but the robot is not connected yet. What we need to do now is we have the targets, we have the tool, we need to create the inverse kinematics. We have set up basically X, Y, Z coordinates, A, B, C, how and where to go. But we need to do translation to actually the axis rotations. It's really difficult to do this. So we have the kinematic calculator. That is create a program. I think it's here. Create speed, create program is one of these ones. Kinematics. Yes. Program. Yeah, it was here. So we're gonna set up a name. This is the file name. This is test. What is the robot system? What robot are you using? We connected here. Okay. And what are the targets? Where do you want to go? Connected. It says, ooh, warning, errors. Let's see. What are the errors? Okay, first warning. First target motion sends to a joint motion using active rotation. It means this you will get to know, but this means the first movement is not linear. It's random because we have a state. But what are the errors? Axis 5 outside of the permitted range. What this is happening? What is this? And you see the robot is not there, doesn't exist. The robot cannot reach that position. And because it cannot reach that position, it cannot show us how the robot will do the movement. And why can you do the movement? Think about the planes. Let's disconnect. No, because the planes are not reachable. Let's move it. Start to showing why is not previsualization the code. Wait. Because we don't have this one. That is the program simulation. Sorry, I forgot to take one of the previews. So this is the kinematics, but not the program simulation. Time. We need to put a slider. That is the total amount. Okay. This is to visualize the robot. You have seen the robot is located there, no? The robot appeared because here, this calculates the program and the code of the robot. This is actually the robot file. It's a little bit complex to understand, no? So, this is what we will save in a pen drive and copy to the robot. But in order to do that, to visualize what the robot will do and how it will do it, humans, we do it visually in general. So we do a program simulation. We connect the program with program and the robot appears. And we have a time. Time is we can set up a slider from 0 to 1. 0 is the initial position, 1 is the final position, always. So we put a slider from 0. We don't want to be 0, 1. We want to be 0.00. So we can see all the small movements. 0.00 to 1. If whatever slide you connect here, it will automatically show to time in general. No, depends on the plugin. This one doesn't do this. KUKA does. So, for example, now we can see how the robot will reach the movement. What's happening? It's weird, no? It's a little bit weird. Let's disconnect the why the tool that is this guy, we have it like this. It's perfect, no? The pyramid is aligned on the XY. What is the XY of the robot? Is the tool, is here. We can see it here. The origin, the pyramid is located in the origin. And the point that was the origin that we have set up here is actually matching also the planes that we have matched, no? But why is not attacking from the top? Exactly. So we have set up that the robot, this is the plane that we are getting. The tool is like that. And we have set up to do also this plane. So the robot is trying to match the plane. So if we want to do it like this, we need to inverse the plane. We need to reverse the flip of the plane. This plane is XY, but the normal is Z plus. We need to do Z minus. So if instead of, for example, having an XY plane, we set up a YZ plane, this plane, instead of this one, the robot will attack on the front. And you see that the robot is slowly adapting for the first positions all the time. And with the slider, we can see from the first position to the last position. And you see, you see that, red warning. Let's see what's happening. Axis 4 outside of permitted range. It means one of the axes is not the object that you want to do, it's in an uncomfortable position for the robot. So either we change the position of this, or sometimes what we need to do is build another plane. And how and why we do that? Doesn't matter if your pen is like this or like this. No. But for the robot, it could be really uncomfortable to do this than this. So what we can do is rotate the plane on its own axis. Let's see it in a simple way. Let's keep with the XY origins. Okay, as you see, the robot is reaching from the top. It's actually hitting itself. It's a silly robot. We need to reverse the plane. Let's reverse the plane. Reverse or deconstruct the plane. Construct plane. That is something that we do a lot. We take the plane and we have the set that is positive. Let's do negative and construct again the plane. So basically we are reversing the plane. Oh, this one is so silly. Yes. Or flip plane or adjust plane, normal direction. Oh, in this case it's easy. We have the plane and the normal is, what is the new normal? -1, negative z. We can create a vector that is z and make it negative. I will make a little bit more space. So we create a plane and we're gonna adjust the plane to another vector. Now we have the plane with the z negative. We just flip it and we connect it. Now it's exactly the same plane, but flip it. Instead of the Z pointing up, it's pointing down. As the vectors, the normal of the planes are not visual, we can do some tricks. For example, do vector display. It will visualize the vector. For visualizing a vector, we need the vector direction and the location of the vector. Where is the location of the vector? The plane. And it's really small here. Can we make it bigger? Arrows, screen, the font size, the screen size. Some components are bigger than other ones. Vector display X. No, it's this one, actually. So we can point, we cannot make it bigger in an easy way. So if we didn't have this, what is the plane direction? It's 1, the vector really pointing up. So the most difficult part of using robotic arms is actually how you make the planes. It's the only thing that is difficult. How you orient the planes.
One question I have, like, so what you've done is you have like 1, 2, 3, 4, 5, 4. So if you wanted to do 1, then up and down to 2, and up and down to 3.
You need to create those positions. You need to create those positions. So yes, you want to do that. For example, what you could do is this depends if you want to do everything in Grasshopper or everything in Rhino. The problem with doing everything in Rhino is you cannot easily change things. That's one of the main reasons why programming is usually done in Grasshopper. Because if you need to change, for example, the spacing of the planes, if your design is parametric, you do it like this. If your design is not parametric, you will need to move each one of the individual points. Let's say you want to do that. I will hide this, and let's build points. I will lock this line, lock. Let's build some points. Point, 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 point. And you want to make the vertical movement. So that means you want to duplicate the points and say movement, down, movement, down, movement, down, movement, down. No? More or less. So what you can do now is reference those points. Points, set up multiple points. And here is really important the order you do the points. You select them. 1, 2, 3, 4, 5, 6, 7. You see, this is actually the line that the robot will do.
You define the sequences.
You define everything.
Otherwise, it just goes.
No, exactly. You define everything. And that's the tricky part. Enter, and instead of creating the points, let's use these ones. Let's visualize. You see, the good point is once we have the setup ready, it's just changing the file is relatively easy. Depends on how you make the file is the important part. So we can visualize robot is. That's why most of the times you don't want to start with points. Last week, 2 weeks ago, you started with like the paste printing a little bit, no? What we did, a simple geometry. And what we did with the geometry? We slice it, we contour it, no? We cut it. And with the cutting, the plugin that we used was actually breaking up in points. We can do the same here. Let's create a cylinder or whatever, a cylinder like that. And let's make it a little bit fancy. Okay. This is a super simple geometry. How we embed it into Rhino, this guy. Geo, no? We reference it, right click, set one geometry, perfect. Now, what if we want to print this? We need to cut it, no? And the cuts are going to be lines. And the lines, we can divide it into points. And the points, we can assignate planes. So basically, you need to deconstruct whatever you want to do into the smallest element that is always a point and then a plane. So let's contour it. Contour is takes your component and cut it. It cuts what? Your geometry based on a direction. What is the cutting direction? In this case, it says 0, 0, 1. It means the plane is cutting in XY plane. Let's cut in XY plane, or actually we don't send the plane, we send the opposite, the normal, the direction. What is the distance of cutting? Let's cut each 5 millimeters. Oops. We have all the cuts, no? Let's cut slightly bigger so it's easier to see. You will see that when you have this kind of geometry, you have thousands of millions of planes. Let's do it in a parametric way. If it works for 5 lines, it will work for 200 lines. When the script is finished, we can come here and adjust it. But we want to calculate the least amount of components as possible, so it goes fast. Let's hide this geometry, so we don't need to see it now. Okay, and let's hide, well, let's not hide it. We have these lines. What we want to do now? Divide them, no? Let's divide the lines into curves. Sorry, the lines into, divide the curves into points. So we have all these points. With the points, what we can do? Planes. We have the components plane here. Let's hide the planes because it's really messy. What the robot will do is this is what we're going to do next week, in 2 weeks. The point is to make this, how you create your geometry is what matters, not what to connect. What happens if we want to create a non-planar? That is a little more complicated because that means your curve needs to be three-dimensional. If you want to print like this, create this movement, it means your points are located three-dimensionally too. Right now we are printing points and going one up and one up and one up. But this curve that we have created is non-three-dimensional. So that will be a non-planar 3D printing. Do you have questions up to now? A lot. I suppose you have a lot of questions. Okay, guys, don't worry. Like, this is really complex to understand. Like, I know that sometimes I explain it like, no, it's easy. No, it's not. No, it's not. No, it's not.
There are other software to do that, except from the
There are. Blender, I think it could, but I've never tried. I don't know anybody here that has tried. Well, no. Fusion 360 has like post processing for CNCs and laser cuts and 3D printers, but not for robotic arms. Robotic arms are like in manufacturing, it's like another league completely. There are not so many components. Guys, what we can do is, well, maybe first, are you still interested in learning how to use robotic arms? First question. Okay. That's why this year I'm pushing to start way sooner. So we have a lot of time to actually trial and error. So you get used to a little bit how to make files. is not obvious at all. Like Josep still knows how to switch on the robot, but not how to make files like completely. And he comes to all the clubs.
So one thing that maybe I learned from this session is that everything is super predefined, right? Like you define everything. So, is there any kind of automation that
No,
happens?
but that also doesn't happen for the CNC, neither for the laser card, neither, well, the 3D printers, yes, because right now they are making so dumb for kids, but if you want to go deep into 3D printing, you do it like this. Actually, this is this. In here, you don't design the geometry. Like these guys, actually, for example, one of the points of this program that is really beautiful on this own, like the OTF, is really bottom up. First week is they build their 3D printers, and during 1 month, they just keep understanding how to create movements, X, Y, Z movements, manually. Like they basically draw lines and understand how they can put one line on top of each other at the correct distance so it prints well. When they have mastered the printers, they jump onto the robots and a new game starts. Like now we introduce A, B, C. Actually, the geometries that you see are lines in the space. For example, this, I don't know if I have the file, but actually we have last week file, no, for the cup. That one, the one that is on the paste printer, is. Oof. What? Oh, Paco, sunrise. 13 de noviembre. For example, you see this geometry, this it's not there. So how to make this is making the line of the path automatic. This geometry was not a solid, didn't exist. Can we produce this with a solid object? Actually, the plugin that you use for face printer is kind of the more approximate, simplified way to do it. What it does is you produce geometry, it cuts. But even if it cuts, it doesn't cut the same as when you do the path on their own. Sorry? Yeah, it's clay. So for example, this, not obvious, for example, last week, I have this file from this is last week. This file is my PSD. I was making a new tool. I just spent like for calibrating the new tool, I spent like 1.5 hours for calibrating. And you see on the black board there, the 5 lines, 2 hours calibrating for doing 6 lines. But it's a new tool, like, and you will not do the calibration. The calibration is one of the most difficult parts, and it's experimental. For example, this tool is super easy to calibrate. Has a point, and it's really easy. We do it, and in 5 minutes, you can set up to print like files like the one that we just created, like this one. What is the important part here? For example, this is a simple geometry. It's more or less a loft. What is the important part? The contour height, no? And more or less, we know that if it's a 1 millimeter nozzle, it's half of it, so it's half millimeter cut. So 3D printing this will be cutting this by half. And instead of taking half second, it's going to take like 20 seconds, more or less. Because it needs to calculate now, instead of 5 lines, oh, actually 1 second, oh, that's fast. We have all these points, and we have divided just like this. What happened with these points? We are transforming a curve and dividing into points. You see this curve, no? This is not a curve. If you just make straightforward the movements between them, what you will see. Let's see in slowly. Wait. We don't see it really slowly. But the robot is making a straightforward movement between these 2 points because it's a linear movement. Let's reduce the points to see it. Count. It will be polygonal. How we can previsualize this? We have cut the curve. We have points. What you can build is a polyline, not a curve based on the points. Just for visualization purposes. Polyline. So actually what the machine will do is hide this. Close it. So what it will do is polygonal. So what is one of the important points in here? Depends on the scale that you print. The distance between the points needs to be larger or smaller. For example, these guys, the minimum distance between the points is 5 millimeters for them. 5 millimeters at this scale, instead of a cylinder, is a polyhedron. So it will depend. When you do a smaller start, you need to put more points. So instead of dividing the points by 10, let's divide it by 40. So increasing the count, there is a moment that you don't see an augmenting quality, and what you are doing is just making larger files in the robot because we don't see any difference, but we need to actually make the points. We are actually seeing the points. But there is a moment that becomes polygonal. So it's always a fight between quality rise versus large files. This is just a line. Imagine this if you want to print an object like this. At 0.5 millimeters high, this is around 60,000 points at this scale. But if you want to print a larger scale with the same height, if your nozzle is 5 millimeters, your polygons, this distance is higher. So you need to you can set up more space so you can reduce layer points, layer count. Yep. Actually, that's something that we don't know why it's like that. Suppose it should have a reason. We don't know what. Like Alex, the guys with more experience with robotic arms is Kunal and Alex Dugor, and they have like more than 10, 12 years experience with robotic arms. And we talk with KUKA developers sometimes, and we don't know why it has that short memory. The main thing is we can guess is like it's for industrial purposes, and the memory count doesn't have to be huge. And what you want to do is like hardware stability. So less memory, less prone to store large files, to have memory corruption, etc. For example, the new generation of robots, what is called collaborative robots, there are robots that you can feel. So the robots, like a machine, doesn't feel. The generation of robots, and actually one of the robots that is there, for example, EOR, then collaborative robot. This kind of robots, it's called so collaborative robots or cobots. Last year we have another one, Eva Kupka, that is cool. No? Evie? So what is a collaborative robot? Is a robot that is designed to work with humans without a safe cage. You see that robot is in a box. That box is called a safe cage. It means the robot, when they are inside, you see that always someone is handling the remote. The remote has 3 buttons. And in order for the robot to move, you need to be pressing them all the time. If you don't press, the robot keeps the electricity off and breaks the motors, locks the position. It's called the deaf man switch. So, in case the robot moves and hits you, you get desmayado. You faint, you release the buttons, the motor shuts off. In case you get electroshocked, what happens when you electroshock? You press your hand, you close it. The button has a extra sensor switch that you press also locks. So it's called the dead man switch. So actually the guys using the robot, there's always one holding the remote, checking and that nobody is getting hurt or dangerous situations happening. When the robot has an automatic mode, that means you just launch the file and you click press. In that case, the robot cage, the door needs to be closed, and we need to lock with a key and activate 2 extra safety switches. So the robot, if you go inside and hits you, doesn't know it hits you, kills you, literally. So cobots are robots that have sensory, an extra sensor. Actually, this is quite new. It's like late this year. So the robots have force feedback sensors. The motors knows the amount of force that they are putting to move or to press on an object. And some of them, they have also on the metal case, they have pressure sensors. So if you press them, they stop. They are human safe. They don't need to work in a case in automatic mode. So the robot could be moving, and if somehow you press it and you push it with your hand, the robot stops. So these are a generation of robots, and also they can feel the amount of force that they are pushing. And actually, one of the robots we have there is like that you can let it, for example, to paint with a brush and set up, I want a maximum load on the brush of 0.2 newtons. And the robot will be adapting the force on the motor to only press that amount. Like they are way better, but also like 3 times more expensive in general. So these robots are for collaborative with robots, and they are better. And but at the same time, as they are meant to have like a more not that industrial use, memories are huger, are bigger, because these robots could also be trained in an easy way. That is, can I have your arm for a second? Can you hold it? You can be the robot and be in teaching mode, and can put the teaching mode and say, okay, you need to do this movement, you need to do this movement, and you need to do this movement. And click memorize, and it will repeat the movement. It's super cool. But also, for example, I don't know how to program it like that. Only one of them. This one, no. Like only in the other building are 3, only one of them. And actually, that robot up to now is only for staff because it's just used for research. That robot is more expensive than that one, and it's half size. But exists. And for example, MRAC, at the end of the year, they use that one. Because, for example, last year they used robot for predicting, like, use robot for massaging. Actually, the final one thesis of them was like someone laying on the table and having a massage by the robot. But until you get to that point that the robot doesn't break your back, it's not that easy. Like they say, you want to trust to do that, like just have in mind that the small robot needs 7 kilos, the other one 15, the other one 20, and this one 150. Like, I should not say, but I have a more. See, a lot of years ago, in summer they use a robot for moving the hammock. I have a photo, not in this one, but in another place, that I'm riding as a cowboy. Like I was in the robot, moving on top of it. And this, a lot of the safety regulations about these kind of things has changed, but I saw something a few years ago, Kuka coaster. Kuka, the manufacturers, like around 10, 15 years, in a promotional like construction environment, Kuka coaster. And they do this with like 0.1 repeatability. It means can repeat the movement with 0.1 millimeters tolerance. This is cannot be done nowadays, but has been done. Okay, also depends on the country. Yeah, also depends on the country regulations, etc. But and this movement is actually what is that? It's a line, three-dimensional line in the space between division of the points and the plane orientation. What happens is the plane orientation is always like normals are always pointing to the robot, so it's always pushing like that. I don't want to extend the session too much. It's already like quite late for lunch. You have more questions? No? For the ones that are still interested and doesn't want to dismiss, we have, especially for the Fall Academy, we'll go over because we will have more grasshopper classes. For the case of NDEF, like we will not see until the next 3D printing like robots. So you want to try to make some sketches at home, we can always review in tutorings. Like if you want to pre-make some files for the next incoming session. Next session is going to be in 3 Mondays, on the 3rd Monday, and we're going to go directly there on the other space. I'm going to show you how we switch on the robot, how we do a calibration, and we will learn how to move the robot. It's going to be a hands-on day, and it will be nice if you have a little file, even if it's just aligning the space of the robot, moving like that, will be nice so we can send it. Like the sessions on the code class are the make labs are quite short. We cannot spend like 1 hour making files. So you can try to have a few files ready. Maybe they are wrong, maybe they are not, no big deal. Like the point is trying to learn. If we can print, that will be awesome. In the worst case scenario, at the end of the session, I can send a complex print to show you how is three-dimensional NOR plan and printing. Okay. The cobots, yeah, Paco, cobots they do surgery. Like, yeah, actually those are the robots that they use for doing surgery. Paco, you want?